Potential games and a global connection game. In this section, we introduced a broad class of games known as potential games. This class encompasses a number of natural and well-studied network-based games. As we will see, potential games possess many nice properties. Pure equilibrium always exists. Fast response dynamics are guaranteed to converge, and the price of stability can be bounded using a technique called the potential function method. Our motivating examples for this class of games is a network formation game called the Global Connection Game, which was discussed in Chapter 17. We begin by defining this game and present some theorems about pure equilibrium and the price of stability. We then introduce potential games and provide generalized results for this broader framework. The network formation game discussed in section 19.2 is local in the sense that a player can build links to other nodes but also has no direct means for affecting distinct network structure. Such might be the case with social networks or peering relationships. In a digital network, the global connection game in contrast models players who make global structural decisions. Players may build agencies through the network and thus consider relatively complex strategies. This game might be more appropriate for modeling the actual construction and maintenance of large-scale physical networks. Beyond the varying scope of player strategies, there are two additional features that differentiate these network formation games. First, in exchange for the global connection game's broader strategy space, we consider a relatively simplified player objective function. In particular, we assume that players are unconcerned with their distance to other nodes in the network and instead want only to build a network that connects their terminals as cheaply as possible. The second notable distinction is that the global connection game supports cooperation in that multiple players may share the cost of building mutually beneficial links. In the local connection game, an edge might benefit multiple players, and yet the edge's cost is always covered fully by one of the two incident players. We now give a formal description of the global connection game. A global connection game, where given a directed graph G equals to V with a non-negative edge cost CE for all edges is E in capital E, there are k players, and each player I has a specified source node Si and a sink node Ti. The same node may be a source or a sink for multiple players. Player I's goal is to build a network in which Ti is reachable from Si while paying as little as possible to do so. A strategy for player I is a path Pi from Si to Ti in G. By choosing Pi, player I is committing to help build all edges along Pi in the final network. Given a strategy for each player, we define the constructed network to be the union of the index I of the path set Pi. It remains to allocate the cost of each edge in this network to the players using it, as this will allow players to evaluate the utility of each strategy. In principle, there are a vast number of possible cost-sharing mechanisms, each of which induces a distinct network formation game. We will briefly touch on this large space of games at the end of section, but for now, our primary focus will be on a single cost-sharing mechanism with a number of nice properties that is both simple and easy to motivate. In particular, we consider the mechanism that splits the cost of an edge evenly among all players whose path contains it. More concretely, if Ke denotes the number of players whose path contains He, then E assigns a cost share of C/Ke to each player using E. Thus, the total cost incurred by player I under a strategy vector S is given by cost I of S is equals to sigma, summing for all E which is in the path Pi of the cost C/Ke. So note that the total cost assigned to all players is exactly the cost of the constructed network. This equal division mechanism was suggested by Herzog et al. In 1987, and has a number of basic economic motivations. Moulding and Schenker prove that this mechanism can be derived from the Shapley 2001 value, and it can be shown to be the unique cost-sharing scheme satisfying a number of natural sets of axioms. See Feigenbaum et al. In 2001, Moulding and Schenker in 2001. We refer to it as the fair or Shapley cost-sharing mechanism. The social objective for this game is simply the cost of the constructed network. One may view this game as a competitive version of the generalized Steiner tree problem. Given a graph and pairs of terminals, find the cheapest possible network connecting all terminal pairs. Indeed, an optimal generalized Steiner tree is precisely the outcome against which we will compare stable solutions in evaluating the efficiency of equilibria. This connection highlights an important difference between this game and routing games. In routing games, such as those discussed in Chapter 18, players are sensitive to congestion effects and thus seek sparsely used paths. But in the global connection game, as with the Steiner forest problem, the objective is simply to minimize costs, and thus sharing edges is in fact encouraged. The two examples in Chapter 17 provide a few useful observations about this game. Example 17.2. See figure 19.3a shows that even on very simple networks, this game has multiple equilibria and that these equilibria may differ dramatically in quality. There are two equilibria with costs k and 1, respectively. Since the latter is also optimal solution, the price of anarchy is k, while the price of stability is 1. It is not hard to show that the price of anarchy can never exist k on any network. See exercise 19.9, and thus this simple example captures the worst case price of anarchy. Our primary goal will be to bound the price of stability in general. Figure 19.3 is an instance of the global connection game with price of anarchy k and a, and an instance with a price of stability harmonic function k. This is in the subfigure B. So in subfigure A, there are 1 and k, and also all the terminals are from the sinks S1, S2, S3 until Sk. They are all the same. T1, T2, T3 until Tk, they are at the same site. But connecting Si to Ti, there are two edges, one with the cost 1, the other with the cost k. And then in subfigure B, again, there are edges and also connecting V to T, and from V to T, in the middle, there are sources. Thus, S1, S2, S3 until Sk-1 and Sk, where S1 goes to T with cost 1, S2 goes to T with 1 over 2, S3 goes to T with 1/3, and Sk-1 goes to T with the cost 1 over k-1, and Sk goes to T with the cost 1 over k. And finally, there are also S1, S2, S3 until Sk that has edges go directly to V, and starting from V, there is a cost from V to T with the cost 1 plus epsilon. Now, example 17.3, see figure 19.3b, shows that the price of stability can indeed exist 1. This network has a unique Nash equilibrium with cost hk, the kth harmonic number, while the optimal solution has a cost of 1 plus epsilon. Thus, the price of stability on this network is roughly hk. Our aim is to prove that pure equilibria always exist and provide an upper bound, the price of stability. Both of these results make use of a potential function, which we will formally introduce in section 19.3.2. Consider an instance of the global connection game and a strategy vector S, P1, P2, P3, and Pk, containing an SI-Ti path for each player I. For each edge E, define a function VE of S mapping strategy vectors to real values as phi of S is equals to C times H of KE, where KE is the number of players using HE in S. And HK is sigma summing for all index j from 1 to k of the term 1 over j is the kth harmonic number. Let phi of S is equals to sigma summing for all edges E of the term phi of S, where we just define that as C times the harmonic function, a harmonic number. And while this function does not obviously capture any important feature of our game, it has the following nice property. Lemma 19.7, let S equals to P1, P2, P3 until Pk, and let Pi prime not equals to Pi be an ordinate path S for some player I, and define a new strategy vector S prime, which is equals to S minus I as the adversary with Pi prime. Then phi of S minus phi of S prime is equals to Ui of S prime minus Ui of S. Proof. This lemma states that when a player I changes strategies, the corresponding change in phi dot exactly mirrors the change in i's utility. Let key ke be the number of players using e on the s for any edge e that appears in both or neither of pi and pi prime. The cost paid by I toward e is the same under s and s prime. Likewise, phi e dot has the same value under s and s prime. For any edge e in pi but not in pi prime, by moving from S to S prime, I saves and thus increases her utility by CE over KE, which is precisely the decrease in phi E dot. Similarly, for an edge E in Pi prime, but not in Pi, player I incurs a cost of CE divided by KE plus 1 in switching from S to S prime, which matches the increase in phi E dot. Since phi dot is simply the sum of phi dot over all ages, the collective change in player i's utility exactly the negation of the change in phi dot. We also note that phi of S is closely related to cost of S. The cost of the network generated by S. More precisely, consider any edge E used by S. The function phi of S is at least CE. Any used edge is selected by at least one player, and no more than hk, the harmonic number of k, times CE. There are only k players. Thus, we have lemma 19.9, which is equals to the cost of S is less than equal to phi of S, which is also bounded, upper bounded, less than equals to hk, the harmonic kth harmonic number, times the cost of S. These two lemmas are used to prove the following two theorems, which will follow from theorems 19.11, 19.12, and 19.13. Theorem 19.9. Any instance of the global connection game has a pure Nash equivalent, and the best response dynamics always converges. Theorem 19.10. The price of stability in the global connection game with k players is at most hk, the kth harmonic number, and since the proofs of these two results actually apply to a much broader class of games, such as potential games, we now introduce these games and prove the corresponding results in this more general context. General games and congestion games. For any finite game, an exact potential function phi is a function that maps every strategy vector S to some real value and satisfies the following condition. If S is equals to S1, S2, S3 until Sk, where Si prime is not equals to Si, is an alternate strategy for some player I, and S prime is equals to S inverse and Si prime pair, then phi of S minus phi of S prime is equals to Ui of S prime minus Ui of S. In other words, if the concurrent game stayed in S and player I switches from strategy Si to strategy Si prime, then the resulting savings I incurs exactly matches the decrease in the value of the potential function. Thus, lemma 19.7 simply states that phi is an exact potential function for the global connection game. It is not hard to see that a game has at most one potential function. Modulo addition by a constant, a game that does not possess an exactly potential function is called an exact potential game. That does possess an exactly potential function is called an exact potential game. For the remainder of this chapter, we will drop the word exact from these terms. See exercise 19.13 for an inexact notion of a potential function. A surprising manner of interesting games turn out to be potential games, and their structure has a number of strong implications for the existence of and a convergence to equilibria. Theorem 19.11. Every potential game has at least one pure niche equilibria, namely the strategy S, that minimizes phi of S. Proof. Let phi be the potential function for this game, and let S be a pure strategy vector minimizing phi of S. Consider any move by a player I that results in a new strategy vector S prime by assumption phi of S prime is greater than or equal to phi of S, and by the definition of a potential function vector S prime. By assumption phi of S prime, which is greater than or equal to phi of S, and by the definition of a potential function ui of S prime is equal to ui of S, which is equal to phi of S minus phi of S prime. Thus, I's ability cannot increase from his move, and hence S is stable. And going one step further, note that any state S with the property that phi cannot be decreased by altering any strategy in S is a Nash equilibrium by the same argument. Furthermore, best response dynamics simulate local search on phi. Improving moves for players decrease the value of the potential function. Together, these observations imply the following results. Theorem 19.12. In any finite potential game, best response dynamics always converge to a Nash equilibrium. A last abstract characterization of potential games can be found in a class of games called congestion games, proposed by Rothenthal 1973 and also in our previous videos. A congestion game has k players and n resources. Player I has a set Si of allowing strategies, each of which specifies a subset of resources. Each resource J has a load-dependent cost function Cj of x, indicating the cost exerted by any player I whose chosen strategy includes resource J if there are x such players in total. The goal cost charged to player I who chooses a strategy Si is simply the sum of the costs incurred from each resource in Si. Thus, if the total load on link J is xj, then I pays sigma j in Si of the term Cj of xj. The global connection game is clearly a congestion game. Agencies are resources. Si, Ti paths are allowable strategies for player I, and the cost function are as C of x equals to Cx divided by x. And Rosenthal 1973 proved that any congestion game is a potential game. See exercising 19.15. Moderer and Shapley 1996 proved that this converts. For any potential game, there is a congestion game with the same potential function. We now present a generic upper bound on the price of stability of an arbitrary potential game. The potential function method and the price of stability. Suppose we have a potential game G with a potential function phi of s and a social cost function c of s. If phi of s and c of s are similar, then the price of stability must be small. We make this precise in the following theorem. Theorem 19.13. Suppose that we have a potential game with potential function phi, and assume that further that for any outcome of s, we have cost of a slash by s, which is less than equal to phi of s times, which is less than equal to b times cost of s. For some constants ab greater than 0, then the price of stability is at most ab. Proof. Let s to the n be a strategy vector that minimizes phi of s. For lemma 19.11, s to the n is a Nash equilibrium. It suffices to show that the actual cost of the solution is not larger than that of solution S star of minimal cost. By assumption, we have that cost of s to the n divided by a, which is less than or equal to phi of s to the n. By the definitions of s to the n, we have that phi of s to the n is less than or equal to phi of s prime. Stringing these inequalities together yields cost of s n, which is less than or equal to a times b times cost of s star as desired. Note that this result, taken together with lemma 19.8, directly implies theorem 19.10. This technique for bounding the price of stability using a potential function is known as the potential function method. And in general, outcomes that minimize the potential function may not be the best nor Nash equilibrium, and thus this bound is not always tight. See exercise in 19.14. However, in the case of a global congestion game, we have seen that the price of stability is at least hk. Thus, for this class of games, the bound given by the potential function method is best possible. Note that we have essentially clearly seen the potential function method used in the non-atomic selfish routing game in chapter 18. For this routing game, all equilibria have the same social topics, the same social value, and hence the price of anarchy and the price of stability are the same. Because of this, theorem 18.16 is phrased as a statement about the price of anarchy, but we can still view this result as an application of the potential function method. In the last section of this chapter, we will see yet another application of this technique for a potential game that models comparative facility location. We have seen that potential games have pure equilibria and that the price of stability can be bounded via the potential function method. We now consider the complexity of finding these equilibria in general position games. Potential games. Finding natural equilibria in potential games. Theorem 19.12 provides an algorithmic means of reaching pure equilibria in potential games. Unfortunately, this theorem makes no claim regarding the rate of this convergence. In some games, best bounce response dynamics always converges quickly, but in many games it does not. In some games, the potential function phi can be minimized in polynomial time, but in others, the minimization problem is NP hard. To get a better handle on the complexity of finding pure equilibria in potential games, we consider the closely related problem of finding local optima in optimization problems. The class polynomial local search problems (POS) was defined by Johnson et al. 1988 as an abstract class of local optimization problems. First, let us define a general optimization problem, say a minimization problem, as follows. We have a set of instances I, and for each instance x in I, a set of feasible solutions f of x and a cost function c of s defined on all s in f of x. We also have an oracle or a polynomial time algorithm that takes an instance x and a candidate solution s and checks whether s is a feasible solution s in f of x or not. If it is, the oracle computes the cost of that solution, cx of s. The optimization problem is to find a solution s in s star. S in f of x with the minimal cost cx of s for a given instance x in I. To define a local optimization problem, we must also specify a neighborhood Nx of s, which is subset of f of x for each instance x in I and each solution s in f of x. A solution s in f of x is locally optimal if cx of s is less than or equals to cx of s prime for all s prime in Nx of s. The local optimization problem is to find a local optima s in f of x for a given instance x in I, a local optimization problem, is in PLS if we have an oracle that, for any instance x in I, and the solution s in f of x, decides whether s is locally optimal, and if not, returns s prime in an x of s, which cx of s prime is less than c of cx of s. Fabricant et al. 2004 show that finding a Nash equilibrium in potential games is POS complete, assuming that the best response of each player can be found in polynomial time. To see that the problem belongs to POS, we will say that the neighbors and x of s of a strategy vector s are old strategy vectors s prime that can be obtained from s by a single player changing his or her strategy. By definition, a potential function phi is locally optimal for cost function cx of s, which is equals to phi of s, if and only if it is a pure Nash equilibrium. So finding a pure Nash equilibrium is in POS. A problem in POS complete if it is a problem is POS complete if it is in POS, and there is a polynomial time reduction from all other problems in POS such that the local optimal of the target problem corresponds to the local optimal of the original one. Since the introduction of this class in Johnson et al. 1988, many local search problems have been shown to be POS complete, including the weighted version of satisfiability, which is by Cranto in 1989. The weighted satisfiability problem is defined by a formula in conjecture normal form C1, C2, and so on until Cn with a non-negative weight Wj for each cluster Cj. Solutions S are true assignments of variables, and the associated cost C of S is the sum of the weights of the unsatisfied clauses. The neighbors of a true assignment S are the assignments obtained by flipping a single variable in S. Here, we show via a reduction from this weighted satisfiability problem that finding a pure equilibrium in potential games is PLS. Complete. Theorem 19.14. Finding a pure natural equilibrium in potential games, where best response can be computed in polynomial time, is POS complete. Proof. We have argued that finding a pure natural equilibrium in such games is in POS. To see that the problem is POS complete, we use a reduction from weighted satisfiability problem. Consider a weighted satisfiability instance with k variables x, y, x2, and so on until k, xk, and the n closest c1, c2, c3 until cn with weight wj for close cj. Our congestion game will have one player for each side and one resource for each clause. Player I associated with variable xi has two possible strategies. It can either select the set of resources Si consisting of all clauses that contain the term xi, or Si bar, which includes all vertices. Which all clauses containing the term xi bar, selecting Si corresponds to setting xi to false, while selecting Si bar corresponds to setting xi to true. The main observation is that a clause Cj with Kj literals is false if and only if the corresponding element has congestion Kj. Let Cj be a clause with Kj literals and weight Wj. We define the congestion cost of the element J corresponds to clause Cj as Cj of tau is equals to 0 if tau is less than Kj, and Cj of Kj is equals to Wj. For the strategy vector corresponding to the truth assignment S, the potential function has value phi of S is equals to sigma summing for index j of the term Cj of Ej, where Ej is the number of false literals in Cj. The weight of assignment S is exactly phi of S, and thus the equilibrium of this game are precisely the local optimal of the satisfiability problem. Variations. on sharing in the global connection game. We now return to our motivation example, the global connection game. By definition, this game requires that the cost of any built edge be shared equally among all players using that edge. This sharing rule is natural, arguably fair, and as we have seen, implies a number of nice properties. But is this really the best possible sharing structure? Could perhaps another sharing rule induced even better outcomes? We can view this question as a problem of mechanical design, although here we use the term more broadly than in Chapter 9. Instead of seeking to elicit truthful behavior, we simply want to guarantee that stable outcomes exist and are reasonably efficient. If we want to design games to induce better outcomes, we must first decide to what extent we will allow ourselves, as mechanism designers, to alter the game. After all, suppose that we define a game which players receive a large penalty for taking any path that does not concern with a particular optimal solution. Such a game has pure equilibrium, and the price of anarchy is trivially one, but intuitively, this is not a satisfying solution. This game is too restrictive and fails to capture the decentralized spirit. Of our earlier network formation games. Therefore, our first hurdle is to specify the class of reasonable games that are open for consideration. To this end, Chen et al. 2006 introduced the class of cost-sharing games. This class includes the global connection game as well as similar games with other cost-sharing rules. A cost-sharing game is played on a graph with age costs and terminals SITI. For each player I, a strategy for player I is an SITI path. Given a strategy vector S, cost shares are assigned to players on an edge-by-edge basis as specified by a cost-sharing method, tau E, for each HE. In particular, if SE is the set of players whose path includes E on the S, then tau E of ISE, which is greater than or equal to 0, is cost share assigned to I for E. The total cost incurred by player I is the sum of I's cost shares. We require that any cost sharing method satisfy two basic properties. Fairness. For all I, E, we have tau E of ISE is equal to 0 if I is not in SE. Budget balance. For all E, we have sigma I of tau E of ISE is equal to CE. A cost sharing scheme specifies a cost sharing method per edge given a network, a set of players, and a strategy vector. This definition allows cost sharing schemes to make use of global information, and thus we also consider the special case of oblivious cost sharing schemes, in which cost sharing methods depend only on CE and SE. Note that the Shapley network formation game is an oblivious cost sharing game with the cost sharing method. Tau E of ISE is equal to CE divided by the size of SE for all I in SE. We now return to our question regarding the relative efficiency of the Shapley scheme. In particular, we will show that non-oblivious cost-sharing schemes can provide far better guarantees than the Shapley scheme. Theorem 19.15. For any undirected network in which all players seek to reach a common thing, there is a non-oblivious cost-sharing scheme for which the price of anarchy is at most 2. proof, we define a non-oblivious cost-sharing scheme for which players at equilibrium may be viewed as having simulated Prim's MST heuristic for approximating a mean cost standard tree. Since this heuristic is to approximation algorithm, such a scheme suffices. More concretely, if T is the common sink, we order players as follows. Let player 1 be a player whose source S1 is closest to T. Let player 2 be a player whose source S2 is closest to the set TS1, and so on. Define a cost sharing method that assigns the full cost of E to the player in SE with the smallest index, since player 1 pays fully for her path regardless of the other player's choices. At equilibrium, player 1 must choose a shortest path from S1 to T, and inductively, the remaining players effectively simulate Prime's algorithm as well. On the other hand, if we restricted our attention to oblivious schemes, Chang, Ralph Garden, and Valiant prove that for general networks, we cannot do better than the Shapley cost-sharing scheme in the worst case. More precisely, they argue that any oblivious cost-sharing scheme either fails to guarantee the existence of pure equilibrium or has a price of stability that is at least HK for some game. Thus, we have an answer to our original question. While there may be non-oblivious schemes that perform better than Shapley cost-sharing, no oblivious scheme offers a smaller price of stability in the worst case. See the notes on this chapter, section 19.5.2, for a brief discussion of research concerning other cost-sharing approaches.